Okay, so this question here says a group of students investigated the relationship between electric power produced and the flow rate of water which is channeled through a turbine. Now, table 1 shows the recorded results of electric power P in units of watts and the flow rate F in units of centimeters cubed per second. And part A in the question actually says we are to calculate the cube of the flow rate readings F3 rounded to 2 decimal places to complete table 1. So I'm going to go ahead right now and complete the table. So now that we have completed the table, right, by finding the value for the flow rate cubed, we can go ahead and move on to part B. So on part B, we're gonna plot a graph of electric power versus flow rate, right? And since we're plotting electric power versus flow rate, electric power will be placed on the y-axis, right? This here, electric power will be on the y-axis and flow rate will be on the x-axis, right? So let's go over to our graph. Okay, so we'll now use the data that we filled out in the table to plot our graph, right? So our first value, well, before we actually start to plot the graph, let's just review what we have done, because I went ahead and filled in some of the necessary information required for the graph, right? So I've already filled in the title, right? I labeled my axes. This is my y-axis, and again I have electric power on the y-axis, and I've chosen a suitable scale, and I've written the scale here. So 2 centimeters is equal to 10 watts. So each 2 centimeters is equivalent to 10 watts. And on the x-axis I've done something similar. I've labeled axis, x-axis, and I've labeled it flow rate. I placed the unit and I placed my scale. So on the x-axis, each 2 centimeters is equivalent to 0.02 centimeters cube per second, all cube. Right? So with that said, I can go ahead and plot the graph. Right? So the first point is when the electric power is 0 and the flow rate is 0. So my first point will be somewhere right here. So I'm going to use dots with circle. So I place the dot and I circle the dot. Now the next point is when the flow rate is 0.02 and the electric power in that case is 13. Now since on the y-axis each 2 centimeter is 10 watt and there are actually 10 lines between the 2 centimeter mark. So what I can do then to find out the value of each line is to divide the number of watts, in this case 10 watts, by the number of lines. So if I divide 10 watts by 10, I get that each line is 1 watt. So it therefore means then that 13 would be somewhere right here, because I have 10 here, 11, 12, and 13. So I'm going to place my dot and again a circle. Alright, next one now is 0.04 right here, and then that match up to 25 and a half. So 25 will be right here, 26 will be right here, so 25 and a half will be somewhere in between 25 and 26. So I can place my point and a circle. Alright, then now I can go further to 0.06, and that's 38.5. So 30 is right here, 35, 36, 37, 38, 38.5, and it will be somewhere right here. And again, I circle the point. Next one now is 0.08, and that matches up to 51. So 50 is right here, and 51 would be right here. So I place my point, and I circle. And then now I move to 0.1, and that goes up to 64. So 0.1, 60 is right here, 65 is right here, so I'm going to be 1 less than 65 to get 64, and my point is right here. And then I circle. And then finally I move over to 0.12, and that corresponds to 77, right? So 0.12 would be in this line, and 75 is right here, 76, 77. Alright, so those are my points. Alright, I've successfully plotted the points. Now I'm required to draw the line of best fit for these points. So I'm going to get my ruler in place. Get my ruler in place so I can draw the line of best fit. And again, the line of best fit is a line that passes through as much points as possible. So let me just zoom out a little bit. Alright, back to my ruler. So I'm going to draw this line. Well, let me get the ruler properly situated. Right, and then I'm going to draw my best fit line starting from the origin. Right, so I'm going to draw my best fit line. So one straight line starting from the origin, going through all the points. Right, so that's my line of best fit. Right, so my graph will look something like this. Alright, so I plotted the graph and I've drawn the line of best fit. So let's find out what else the question wants us to do. Okay, so we're continuing with our question, and this part of the question wants us to calculate the gradient of the graph, which we just plotted a short while ago. So let's revisit that graph. Right, this is our graph here. Right, and we are required to find the gradient. Now, the gradient of the graph is merely the change in the y-axis divided by the change in the x-axis, or another way to put it is simply the rise over the run, right? In each case, the rise occurs on the y-axis and the run will occur on the x-axis. So to find the gradient, the first thing I will do is to make a plot or draw a large enough triangle which covers all the points so I can find my gradient from that. So I'll place the ruler in place. Alright, so I'm going to mark off my points using dotted lines. So alright, so that's the rise. Now let's do the same thing to acquire the run. So I'm going to place the ruler right here. Right, and I'm going to connect with broken lines. Alright, so that's my triangle there. So I'm going to need to determine, because remember gradient, let's call that m, is equal to y2 minus y1 over x2 minus x1. Right? So in this case, let's just write down the y2 values. So y2 would be 84 watts. So that's 84 watts minus y1, which would be, that's 5 watts. And then x2 would be right here, would be 0.13. So 0.13 minus, and the y1, not y1, x1 would be, say, 0.01, so 0.08, 0.008, so 0.008. These are my values here, and I'm gonna let's just copy this over. Just copy. Alright, so once we have this in place now, we can simplify the gradient. So we will say 84 watts minus 5 watts is 79 watts, right? And then 0.13, let me just use a calculator to do that. So 0.13 minus 0.008 equals 0.12, 0.122, right? And then we can find the gradient by dividing these two values. So I'm going to say 79 divided by 0.122, and that is 647.5 watts per centimeter cube per second, and all of this is cube. Alright, now next part of the question asks us to use the graph to estimate the electric power produced if the flow rate F is 0.22 centimeter cube per second. Alright, so for this now we will need to revisit the graph. Alright, so this is the graph. Alright, so this is the graph, and it says that we should estimate the flow rate if estimate the electrical power if the flow rate is 0.22. Alright, so let's just navigate to 0.22. So 0.0, because we plotted centimeters cube per second squared, all cube, we need to actually cube the value we're given, which is 0.22, to find it on this graph here. So when we cube that, we'll get 0.016. Let me just illustrate that. So if we cube 0.22 and we cube that, we will get 0.0106, right, which is somewhere here, right? So let's say the point will be right here. This will be 0.22. Right? So if we extrapolate up, we can read off that the power will be somewhere about right here, and that's 5, 6, 7. That's 7 watts of power, right, when the flow rate is 0.22. So let's just copy that over. Right, so the power, right, is 7 watts. So this is the power flowing, or the electrical power produced when F is equal to 0.22 centimeter cube per second. Alright, so we can go further now to finish our problem. So it says now use the results on part D to calculate the electrical energy in joules produced in 300 seconds. Right, now the formula that actually links power to energy is given as power is equal to energy divided by time. Alright, so in our case we're actually interested in finding energy, so we can rearrange this formula to make energy the subject. So we're going to multiply both sides by time. When we multiply this side by time, time will cancel, and then we can multiply this side by time. So we're left with energy, in this case electrical energy, is equal to power multiplied by time. Alright, so we know the power, right? This is the power, is 7 watt of power, right, is produced when the flow rate is that. So we can use our value for power here. So we're going to write power is 7 watts multiplied by, and it says 300 seconds, and that is 2100 joules. Right, let me just check with the calculator. So 7 times 300 should give you 2100 joules. Right, so that's the electrical energy that is produced when the flow rate is 0.22 centimeters cube per second. This part of the question now says that to determine the flow rate, the students use a stopwatch and a measuring cylinder. Right? State 2 precautions that should be taken to ensure that the flow rate was accurately determined. So the first precaution we will take, since we're using a measuring cylinder, is to ensure that the measuring cylinder is placed on a flat surface. Right? Next thing, we're gonna ensure that the measuring cylinder is read from the correct eye level. Right, so we do this in this case to prevent any parallax error. Right, parallax error. Right, so if we have our measuring cylinder, and again it should be on a flat surface, we will ensure that our eye is placed at the right line of sight. So if the meniscus is right there, we're going to read from the bottom of that meniscus. So these are two precautions that we will take when conducting this experiment. Now the next question says, state the major energy conversion taking place in the turbine. So because we have water flowing, right, let's say we have water flowing just like a pipe. We have water flowing, and the water is flowing under the influence of gravity, right? And we know that when an object is at a certain height above the ground, it has gravitational potential energy, right? That is stored up energy the body has due to being raised at a certain height. So in our case, we were going to have gravitational potential energy, right? That gravitational potential energy will actually interact with the wheels of the turbine, right, to generate kinetic energy, right, and then that kinetic energy will turn those turbines and generate electrical energy. Alright, so we have gravitational potential energy to kinetic energy, and then finally we get our electrical energy. Right, so this is question 1. We're gonna follow up with question 2 and until we complete the paper. So stay tuned for the additional videos on this paper here. Thank you for watching.